We are finally done with our very long journey through all of the applications of the derivative, and we're finally ready to start learning about antiderivatives. And antiderivatives are what they sound like. We're going to be doing derivatives backwards. So we're going to be given a function, lowercase f of x, that is the answer to someone else's derivative problem. So they're going to give us lowercase f of x, and we're going to try to reverse engineer and figure out what function they must have taken the derivative of to get lowercase f. So for example, let's say they tell us that lowercase f of x is equal to 5. We're going to try to find the antiderivative of 5. So we're going to think, what kind of function could we have taken the derivative of and gotten an answer of 5? Well, this usually happens when we've taken the derivative of a linear function where we just kind of peel off that constant multiple. So maybe capital F of x would be equal to 5x. So 5x is an antiderivative of 5. What if I gave you f of x equals 3x squared? So we could think, what could I take the derivative of to get 3x squared? Well, we remember our power rule, so kind of doing it backwards. Maybe capital F would be equal to x cubed, because I take the derivative of x cubed and I get 3x squared. So this gets a little more complicated when they don't give us the exact right coefficients on there. So what if they gave us f of x was just x squared? On the previous example, I give you 3x squared. That 3 was sitting out there as the coefficient, ready to be that exponent that had been brought down out front. Now I still have x squared, but I don't have that 3. So what could I have taken the derivative of to just get plain old x squared? Well, it would have been x cubed. It has to be. That's the only way I get x squared when I do the power rule. But I left a little space there because I have to have something that's going to cancel out that 3 when I bring it down and take the derivative. So what would cancel out a multiple of 3? How about a 1/3? So if I take the derivative of 1/3 x cubed, just to check off to the side here, the 1/3 would go along for the ride, and then I would multiply by the derivative of x cubed. And then that 1/3 could cancel out the 3. Let's try one more. F of x is equal to cosine x. All right, so sine and cosine are each other's derivatives. Usually we think derivatives cosine is negative sine. When we're doing the antiderivative, we're trying to figure out which function has a derivative of cosine. And this is going to be positive sine, because the derivative of sine is equal to cosine. The last thing I want to mention on this slide about antiderivatives, look at that definition. It says a function capital F is an antiderivative of lowercase f. It kind of implies that there might be more than one antiderivative, and there's actually an infinite list of antiderivatives for every function. And the reason why is because we know the derivative of a constant is equal to 0. So this capital F of x function could also have been 5x plus 7 or minus 12 or plus 68.5. You could add on any constant that you want to on the end. And when you take the derivative, it's going to go away. So what we usually do when we find an antiderivative is we add on a plus capital C. So we're going to write plus a capital C. And that plus capital C basically is for a constant, and it's just saying there might be some kind of constant that was added on the function. There's no way for me to know if that was there or if it was, what it was. So we just kind of always put a plus C on the end of an antiderivative. We have some very interesting notation for the antiderivative of a function lowercase f. So the most general antiderivative of lowercase f, capital F of x plus c, is called the indefinite integral of f, and it's denoted with this notation down here. All right, so we're going to call this kind of elongated S symbol, this is going to be our integral sign. You've got f of x, so this is the function that you're integrating. We call this the integrand. And then we have this very random looking dx hanging out at the end of the notation. We're going to spend a lot of time later talking about what that is and why it's there and what it means. For now, just think of it as a partner that goes along with that integral sign at the beginning. The only job it's really going to do for us now is to tell us what the variable of integration is. So here, this would tell us that x is the variable of integration. So if you had a function of t that you were finding the antiderivative of, you would see dt at the end of the integral. If it was a function of theta, you would see d theta. So then the rest of the video, I'm just going to show you a few quick antiderivative rules. And we have this one here that we kind of already figured out on our own on the first slide. This says that the integral, the indefinite integral of k dx is equal to kx plus c. So we saw this when we were trying to find the antiderivative of 5. And we found that the antiderivative was 5x, right? So we found the antiderivative and we found 5x. And again, always put that plus c on the end when you're finding an indefinite integral or an antiderivative. And this could refer to any constant. So you could have negative pi dx, and you would just slap an x on that constant. So we'd have negative pi x plus c. These constant antiderivatives are the ones where you want to pay attention to that variable of integration. So you could have an integral that was 7 dt. That dt tells you that the variable is not x in this case, it's t. So instead of putting an x on the 7, I'm going to put a t on the 7. And again, I could put any variable that I want in there. We could have the antiderivative of 100 dp. So we know how to find the antiderivative of a constant. We just put a variable on there. This time we're going to put a p on there because this notation tells us that's what the variable is. So we would say 100 p antiderivatives, always getting a plus c at the end. This one is our reverse power rule. Normally taking derivatives, we take the exponent down in the front and multiply, and then we subtract 1 from the exponent. Here, when we find an antiderivative, we add 1 to the exponent, and instead of multiplying, we divide. We accidentally worked this one out when we found the antiderivative of x squared. So I was finding the antiderivative of x squared. This rule says whatever that n is, whatever that exponent is, you add 1 to it. So we would take x cubed. And then whatever that new exponent is, that n plus 1, it also shows up as the denominator, which is the 3 in the bottom. And of course, always a plus c. And we had kind of worked out that there needed to be a 1/3 x cubed. That's the same thing. So any exponent that I put on here, if I have x to the, let's see, 3/5 dx, right? So we're going to add 1 to the exponent. Fractions, we always go off to the side, right? So 3/5. With derivatives, we're subtracting 1. With antiderivatives, we're adding 1. So we're going to add 1. We know to make this plus 5/5, and we get 8/5. So my new exponent is going to be 8/5. And we're going to divide by that new exponent. So you add 1 to the exponent, divide by the new exponent. So I'm going to divide by 8/5 plus c. That's a complex fraction. I don't want to leave that 8/5 in the denominator, so I'm going to flip the second and multiply, right? So we're going to reciprocate that 8/5 and multiply. So we would say 5/8 times x to the 8/5. And don't forget our plus c. This backwards power rule works for negative exponents as well. We could have something to the -7th power. Let's change the variable up. Let's do t. So t to the -7th. We know if we change the variable, that's going to change the notation over here, just kind of getting used to that. This says to add 1 to the exponent. So I'm going to take t, adding 1 to the exponent, -7 plus 1, that's going to actually be -6, right? So -6 divided by -6 plus c. That might look a little nicer if I pull the negative out front and maybe move the t to the -6 down to the denominator, but we can leave it there. Notice that the only exponent this doesn't work for is -1, and look why. So if I try to do this over here, if I try to find the antiderivative of x to the -1, then I would end up adding 1 to the exponent, which would give me -1 plus 1 is 0. And I'd have to divide by 0. That doesn't make any sense, right? So you're going to learn in Calc 2 how to find the antiderivative of x to the -1. You'll be far beyond this class when you finally solve that mystery. We talked about how the antiderivative of cosine was equal to sine. The antiderivative of sine is going to be negative cosine. This is kind of irritating that you have to remember that the negative signs switch places when you're going from derivatives to antiderivatives. But again, remember, we're trying to find the function that you could take the derivative of and get back to the answer in the integral notation. So if I took the derivative over here, that negative would go along for the ride. We know the derivative of cosine is negative sine. So that negative sign on the antiderivative is there to cancel out the negative that's implicit in that derivative of cosine. Those two cancel out, and that's why you get that positive sign. So we'll just have to remember this. Sine and cosine are each other's derivatives. They are also each other's antiderivatives. We just got to keep the negative signs in the right place. Lastly, I have a pile of other trig antiderivatives. These are going to be the only ones that we can calculate for now before we learn some more sophisticated techniques. Basically, I've just taken the trig derivatives and rewritten them as integral rules. So because the derivative of tangent is equal to secant squared, the antiderivative of secant squared is equal to tangent, and so far on down the line.